Welcome back to the part 2 of lecture number 12. So, we have been talking about processing of materials, and we started discussing about solidification processing. How can you shape or get a components from the liquid state, right? And this is the last slide I shown you. You can see here the fundamental factors, right? So, we talked about factors like fluid flow, heat transfer are critical aspects, critical factors for determining the solidification processing. Let us talk about temperature or the heat extractions. And if I take a pure metal, let us talk about pure copper, and I have a liquid of copper, start cooling it down. How this cooling curve will look like? That means as a function of time, how the temperature will change, right? That is what is called a cooling curve. You have to understand that. As a function of time, how this cooling curve will look like, that is what we have to take. So, this is the y axis is temperature, x axis is time, and it start cooling from liquid state. You can clearly see it cools down, still reaches point B, and point B is correspond to its melting temperature of copper. That is, chemical temperature of copper is how much? Anybody remembers? Is 1084 degrees Celsius. So, but you see it is at the temperature, still nothing is going to happen. Temperature still is going down, so it reaches the point C. Then again temperature will increase further, increase to point B, and it remain constant for large length of time. Finally, again it decreases. So, I have marked this part as L, this part as S. You can clearly see that S and L, right. So, now why this dip of temperature happens and again it rises? That is something new, unique, right? That is something new. Well, at the melting temperature, there is no driving force for the system to go from liquid to solid state. At the melting temperature, driving force is 0. As you know, you need to have certain kind of energy or driving force for the system to go from liquid to solid state. That is why the liquid needs to be cooled below the melting temperature, and that is what is known as undercooling. You can clearly see BC corresponding to undercooling, right, and AB is above the melting temperature, that is what is called superheating. So, now once you undercool, you provide the system some energy, and with that energy system will get some driving force to transform from liquid to solid. So, this is from lay points of view. So, nucleation, as you know, it is not a very easy phenomenon to understand. Is basically nucleation means temperature going down and you are undercooling, so giving the system certain amount of energy to form the nucleus or nuclei. After it has the solid has nucleated in the liquid, okay, like if you can easily consider even water and ice system. You take water, start cooling down, at 0 degree Celsius temperature, water will never transform to ice. You have to cool down below 0 degree Celsius temperature to form this ice crystals inside the water. Once it is formed, then they will keep growing, and that is what is shown in the red region, where the temperature remains constant. That is what is called the solidification, or the solidification growth of this nuclei in the material. And after everything is over, temperature will go down further. So, this is a very simple cooling curve, right, very simple looking. Important aspect is here. So, you have a nucleation of phase taking place, nucleation of solid from liquid taking place, right, and that is why you need some undercooling. I will not go into the energetics of the systems, that is available in standard textbooks also. So, now I show you 3 pictures here. Okay, first one left side, when there is no undercooling, this is an ideal situation which will never arise in real life. Okay, if you want to process any material, the first curve I, okay, first one is never going to happen, because you need to provide energy to the system to transform from liquid to solid. Without that, it cannot, correct. Now, the second one is more realistic, that is what I discussed in the last slide, right. Now, what is the third one? This is the third one. What is the third one? Third one is for alloys, that is not for pure metal. So, how it will happen? Let us see the next picture. Let us talk about this kind of simple phase diagram. We talked about some phase diagram in the last few lectures. Let's talk about a simple phase diagram like this is for copper, maybe nickel and copper, yes, nickel and copper. Nickel has melting temperature of 1452 and copper is 1084. So, they form this kind of phase diagrams. Now, if I have to plot the cooling curve, temperature versus time plot, you can clearly see there is no such thing like a dip temperature at the melting temperature, because melting temperature corresponds to the liquidus temperature here, solidification temperature corresponds to the solidus temperature here, marked here. Between B and C, B corresponds to TL liquidus and C corresponds to solidus TS. So, it continuously drops. So, that means nucleation does not happen. Well, it happens. As you clearly see in the liquid plus solid region, the temperature is changing. As the temperature changes, composition changes. That is why the curve looks like this. So, nucleation can be observed, nucleation dip can be observed when you take a pure metal, but it cannot be observed when you are solidifying a alloy. That is what we are trying to say. So, this is a feature which is very important. Now, since we talked about nucleation, let us talk about what are the different stages of solidification of any crystalline material. Well, first thing is formation of nucleus. What is nucleus? Nucleus is nothing but some cluster of atoms which can come together and form a regular array of arrangement of atoms. Do you remember crystalline structures, right? Their atoms are arranged in a regular manner, very regularly ordered manner. So, in the liquid everything is haphazard, because there is no crystalline structure in the liquid, right. But during nucleation, nucleation is a fluctuation process or stochastic process. In some part of this whole liquid, these solid atoms will align in a regular order manner. That is what is called nucleus. So, once this nucleus will form, and they can form anywhere in the liquid, or they can form some specific location also, that we will talk about a little later. So, then this nuclei in the second stage B, this nuclei will grow. The growth is means what? Attachment of atoms to the nucleus, and then once they grow, fully grown, all these nuclei which are growing, they do not know each other, right. At the beginning they will hit on each other and form boundaries, and these boundaries are called grain boundaries, you can see here. So, this is in a nutshell what will happen in solidification. In solidification, this kind of crystals will start forming as a nucleus or nuclei, line of nuclei, then they will grow and form boundaries, and then you see this grain structure in actual under microscope. That is what is in a nutshell is something which you should know. So, you understood there are two important basic aspects happens during solidification. One is nucleation, other is the growth. Nucleation is nothing but formation of this tiny stable solid particles from liquid, and you see it is written even in this thing is the number of atoms may be 50 to 60 or 100 atoms maximum. So, size of this nuclei is very small, couple of nanometers, right, in diameter. And as we talked about it, about this cooling curves, undercooling is fundamentally required to create energy between solid and liquid interfaces. You see here this nucleus is solid and outside there is a liquid, therefore, there is an interface between solid and liquid, right. Liquid atoms are haphazard at random, solid atoms are orderly, arranged in an orderly manner. So, you need to provide that energetics between the solid and liquid. Where from the energy will come? Energy is coming from undercooling of the liquid. That is why you need to undercool the liquid to provide the energy for creation of the new solid liquid interfaces. And larger the extent of undercooling, greater will be number of nuclei will form, finer crystal size will be forming. If you want a finer grain size, you have to provide more driving force. Now, nucleation can be two types. One is heterogeneous, other one is homogeneous, right. Heterogeneous is what is observed in real life. Heterogeneous means what? Nuclei can form on a solid surface, like on the walls of the mold, some particulate in the liquid, solid particles can be present in the liquid, or even on the surface. So, that means what? Nuclei form basically only preferentially certain sites, whether it is a mold wall, particulates, or the or outside or the top surface, does not matter. Okay, it is in a liquid is in a container. So, therefore, that is called heterogeneous. That means, they are not same everywhere. Compared to that, homogeneous nucleation means nuclei can form anywhere on their own. Now, heterogeneous nucleation is easier to occur. That is why we find them more. If you want to form ice from water in a refrigerator, what do? You take this water in a small container and then cool it down, right, in the fridge, and then you will see the ice crystals will start going from the container wall. That is called heterogeneous nucleation. Now, in a very nutshell, I thought of providing you this picture. Homogeneous means anywhere it can form, and formation probability of nuclei is same everywhere in this volume, but heterogeneous nucleation it is not the same. It can happen mostly on the walls of the container or on the subsurface or some particulate material. That is the difference between heterogeneous and homogeneous. Well, knowing these aspects, so cooling curves, some amount of nucleation. With nucleation is important. Why? Because you have to create different grain sizes after casting. How do you do that? So, let us talk about how metal casting processes, what are the processes used to produce this casting. Remember, there are many processes used. I suggest you to read this book if you have time, S. Kalpajiam and S. R. Smith, Manufacturing Engineering and Technology by Pearson. And this is a very good book if you want to really go through, but I know you do not have much time to go the books, but there will be videos available on NPTEL or some courses available, you can go through that also. So, there are two important metal casting processes. One is called expandable mold, other one is called permanent mold. You must have understood mold means the cavity where you want to create the 3-dimensional shape, right. So, expandable means you can use it at one time and after that you simply destroy it and get out the casting from the mold. That is basically typical sand mold casting. You can use a sand to create a cavity and then cast it. Permanent mold means mold is permanent, you cannot break it down. Obviously, permanent molds are made of metals, right, they must be. And why they are made of metals, not ceramics, because metals have much thermal conductivity, they can take out the heat faster. As you understood, you are solidifying liquid, liquid solidification requires to extract the heat, then only you can make it solid. So, that is why permanent molds are widely used. Now, green sand mold, that is what is one of the expandable molding operations, is what is green sand means you add, along with sand you add some water, some other molasses, some other agents, bentonite clay to make it nice, so that surface finish can be retained. And you can see here we have a ladle, you put the metal inside a cavity that is called sprue, and then you have a runner, you can see this cavity will look like this. These are to control the fluid flow, and then it will go through the grate and come inside this mold cavity, fill the mold cavity, right. But most of the metals shrink during solidification. So, therefore, you have to provide extra liquid, that is why you add a riser, and this riser will contain extra liquid. Once during solidification process if it shrinks, riser will provide extra metal. So, this process is very commonly used in various kinds of engineering and technologies. So, you have probably seen also that, or many of you might have made this kind of molds and seen the solidification happening, not seen, made the casting out of it, right, also. Well, different parts of this molding operation is this, just to show you, this is called a down sprue, then you have a this is the riser here, you see here, and this is what is it. If you want to create a hole like a pipe inside a casting, you can use a core actually. Core is nothing but an extra piece which is attached by this kind of chaplets, basically they are kind of pins, and this to fix it, so that it does not move during the fluid flow, and then liquid will be surrounded by this and they solidify. Then you can create a pipe, a hollow product, you can see this hollow product is creating by this way. Well, as I already talked about it, the engine blocks have many holes, right, they are prepared this way only. You can see here this is one such engine box where so many holes are there, you can see these are holes, so many holes are there. How they will be prepared? They will be prepared by this way only. There are many compressor parts also prepared by castings. Nowadays even the connecting rod can be prepared by casting also. Many compressor parts are prepared there. Well, Rather than that, there are many kinds of molding operations. I will talk about few of them for the time available to me. One is called shell molding. What is shell molding? This is nothing but you have pattern. Pattern can be made of metallic. Okay, pattern means particular shape basically, and then you have a sand with certain resin binders. And first you heat the pattern, and then put it upside down. Whole thing is upside down. You can clearly see in this picture too. Sand will be in contact with the mold, and then sand will then form a shell around it, because it is resin. Resin must have melted, and then liquid resin along with the sand will form this kind of shell. Then you can remove the shell and create different kinds of pattern. You can see here. This is very simple technique which is used in the automobile industries. Okay, in fact, if you visit any automobile in industry which are making castings, they use this kind of processes very widely. Only problem is in this process is to control the heating and also control the shell thickness. Well, there are other expandable process like expandable polystyrene process. What is it? Basically, this is a mold. You can clearly see this is inside a mold. You inject polystyrene beads, easily available in the market, polystyrene beads with a heated aluminum die. This is made of aluminum die which is heated, right? And then what will happen? Then this is pressed. Okay, this die is 2 pieces of the die are pressed. First you put inside is pressed, right? Once you press this, the polystyrene beads will melt, and then you cool it down, they will solidify and form this kind of molds. You can clearly see this mold is easily prepared. Then we can integrate this mold using all this rana, sprue, everything I told you, and then pour liquid and form castings. Very simple process, right? Then after that you have to break out the mold and take the casting out. That is why it is called expandable molding process or expandable polystyrene process. These are nothing but different ways of using different kind of material to prepare this kind of castings. I will talk about another important aspect which is used for ceramics, which is called slip casting. Slip casting is what? First you have to produce a slip. Slip is nothing but a slurry. Okay, this is slurry, nothing but a slurry. And then slip is first poured into a absorbent mold. You can see this is absorbent mold, and if slip is poured inside this. Correct? This looks like a water container, right? And then once it is poured, once it is soaked, a layer of clay forms as the mold surface absorb water. Okay, this is what you see, layer of clay has formed here. And then when the shell is of suitable thickness, excess slip is poured away. Basically it is upside down. So whatever excess is there, that is thrown out. Correct. So you have to allow this slurry to form what? Form some kind of a shell of suitable thickness. That is what is important. And then once it is formed, you take it out, heat it up, make it harder. Okay, simple process, and then you get the mold. You can pour the liquid inside it and get the casting. Very simple, right? This is called a slip casting process, because this slurry is called slip. This is shown here more detailed manner. You can clearly see this was the initial mold. You put the slurry here, slurry will form a thin, you can see that what is formed is thickness, very thin layer, and then this is your mold is. This is widely used in many of the casting processes. Slip casting is used to prepare this kind of cups. This is a wet clay, you can see here, and the freshly cast cup is produced. Then once you fire it these cups, you will get a solid piece which can be sold in the market. That is what it is. Another important process which you will discuss is investment casting. That is what the statues are built. Okay, statues are built by this, because investment casting allows you to prepare intricate shapes. Statues can be built up that, and I am showing you a snippet or snapshot of that. You can clearly see that these are the these are the wax pattern. This is the wax pattern, pattern made of wax. Okay, and these wax patterns are joined like this. This is the whole pipe, and this is the sprue. This is a pipe actually, and they are joined. Now this wax pattern is dipped inside a refractory slurry, and they are dipped, and then after dipping they are taken out and then put sand. Okay, they are showered with refractory powders. Okay, ZrO2, Al2O3, aluminum oxides, and so that these powders will stuck with this slurry, and this process will be happening several times, sometimes 5-6 times. Dip it in slurry, take it out, shower this refractory powder, and allow it to get it cool down or get it covered by this refractory slurry, then again dip it into the slurry. So, once this will lead to formation of a thick cell, okay, around these wax patterns, and then this whole thing is taken inside a furnace, heated up, wax will melt back and come out, and this shell will form the mold. That is what is called invest, okay, this shell, and then you can pour liquid. Once the liquid is solidified in the mold, then remove this shell and get the casting out of it. Very simple process, but very genuine process. So, remember I showed you the statue of dancing girl from 5000 years ago in Indus Valley civilization. This must have been prepared same route like this, because the amount of intricate pictures, you can go back now your video, amount of intricate is there in the casting is so nice and surface finish so good that can be obtained by sand casting. So, that is how investment casting is made. I showed you two pictures, one is this Nataraja statue, other one is the Oscar statue. You can clearly see that how intricate these statues are, and they are prepared by investment casting routes. Then you have what is known as a pressure casting. You can have low pressure die casting or high pressure die casting. What is it? It's very simple. Okay, you can see this is a container or ladle which has liquid, and then this liquid is passed through this refractory tube and reaches this mold, and this mold is retractable. Then two pieces can be separated easily, and by air pressure they allow the liquid to pass through. That is why it is called low pressure die casting. And this mold, which is permanent mold, basically is made of metal, is a permanent mold casting, and these two molds are joined together to make a cavity and allow the liquid metal to go inside the cavity. Once it is filled the whole cavity, allow it to solidify and take it out. An important version of this is called pressure die casting. That is a low pressure die casting is called pressure die casting. What is done here? You pour liquid metal inside this cavity, and then using this injection piston, you can force this liquid metal to go inside this mold cavity and then allow it to solidify. You can do many ways also. You can simply plunge, use a plunger to force the liquid go into the mold cavity. Right, okay. That also you can form this kind of casting. This is a casting you can see, very easily you can see that casting. So, this is widely used. Pressure die casting is widely used in case of auto components which are very thin shells or very good surface finish. Another important aspect is called switch casting. Switch casting is what? Well, this is also similar. What you do is basically pour the liquid from the ladle inside this die and then use a punch to squeeze. So, what will happen is that in between the gaps between this die and the punch, the liquid will take the shape, and that is your casting. Because since you are squeezing using a punch, it is called a squeeze casting. So, there are many such processes available in the engineering community. So, we will not talk about it much details, but we will talk about some very specific things like centrifugal casting, continuous casting, as well as single crystal blade casting in the next lecture, and we will talk about other methods of manufacturing, because I want to complete these things in a couple of lectures so that I can go into the basic aspects of machine learning as quickly as possible. So, with that, let us stop this lecture. Thank you. Hope you are enjoying the lectures, and please go to my references and read whatever associate literature you need to understand. Thanks.